Hey there, physics students. In this video, we're going to review a practice FRQ in preparation for the AP Physics 1 exam. This is a qualitative-quantitative transformation question, which means you have to apply physics principles using algebraic expressions, equations, and also a brief written description. So let's get started. The disk shown above spins about the axle at its center. A student's experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. At time 0, the disk has an initial counterclockwise or positive angular velocity, omega naught, and the disk later comes to rest at time t1. Now, there are a couple of things that they tell us. First of all, they tell us that there's friction between the spinning disk and the axle, and that friction creates a constant torque. That's important. It says it has an initial counterclockwise positive angular velocity, omega naught. So we know that the disk is rotating counterclockwise, and convention says that counterclockwise is positive. So it goes from a positive omega naught, and it later comes to rest. And all that means is that omega final, we can call it omega final if you want, is 0. Okay? So we know that the disk is spinning, it has friction, it undergoes a constant torque, and it goes from some positive speed down to 0. That means it accelerates from a positive speed to 0. That means it's going to have a negative acceleration. So let's see what they want us to do. It says on the grid on the left below, sketch a graph that could represent the disk's angular velocity as a function of time from t0 to t1. On the grid on the right, sketch the disk's angular acceleration as a function of time from t0 to t1. So we've got two things to graph. We've got angular velocity from 0 to 1, and we have angular acceleration from 0 to 1. Now they tell us that it starts out with a positive angular velocity, and so of omega naught. And so we can mark that that positive angular velocity starts out here on the initial velocity. We also know that it ends up being at rest at time 1, so it's going to be down to 0 at time 1. It has a constant torque, which means it has a constant angular acceleration. So that means our acceleration is going to change the velocity in a linear manner over time. So we have a straight line from omega naught down to 0. The constant torque, again, produces a constant angular acceleration. That angular acceleration is going to be negative because it goes from a positive value down to 0, meaning it's moving in the negative direction. So it's a constant angular acceleration somewhere in the negative area. So it has to be below 0 and it has to be constant. In terms of scoring, they're probably going to look for the 2 points, the 2 intercepts, the initial velocity and the final velocity, and a constant slope between them. For the acceleration, they're going to look at some constant negative value below the x-axis, okay, or below the 0 line, sorry. Okay, so let's see what else they have to say. The page gets cut off here, so let's take a look at the next page, and it says the magnitude of the frictional torque exerted on the disk is T naught, or they use a little t, we usually call it a tau, a Greek letter. So the torque is given by T naught or tau naught. Derive an expression for the rotational inertia. We call that the moment of inertia, or the rotational inertia of the disk, in terms of the torque, the velocity, and the time, and any physical constants as appropriate. Well, what do we know? We know that if something is undergoing a torque, we can write an expression for torque equals T, or tau equals I times alpha. And that's right off the AP Physics 1 equation sheet. But this is nothing more than Newton's second law for rotation. Instead of F equals ma, we have torque equals moment of inertia times angular acceleration. What else can we do? We know that if it's accelerating, that acceleration is really a change in velocity over time. So that's omega over t. And now here with these two expressions, we can see we have all the terms that we need. We have the torque, we have the angular velocity, we have the time, and of course we have the moment of inertia, or the rotational inertia. If we set these two, if we plug in, the angular acceleration term into the second law statement, so we would find pretty easily that torque equals moment of inertia times, instead of the alpha, we're going to put omega over t. we do a little algebra and shift some things around, and pretty easily we can see that isolating the I value, we're going to end up with the torque times time over omega. Okay? Okay, let's move on. In another experiment, the disk again has an initial positive angular velocity, omega naught, at time 0, but at time 1/2, meaning halfway through the beginning and the end, at time 1/2, the student starts dripping oil on the contact surface between the axle and the disk to reduce the friction. So we're going to reduce the friction. So that friction that caused a constant torque is going to be reduced. As time passes, more and more oil reaches the contact surface, reducing the friction even further. So let's take a look at what that really says here. Okay, so we know we're going to have this disk, and it starts out moving at an initial velocity, but in this second experiment, in this other experiment, we're going to drop some oil, okay, onto the contact surface so that this surface where there is friction, okay, that friction is going to be reduced by that oil, and it's going to cause that constant torque to not be constant anymore. So let's see how we want to deal with this. Okay, so it says, on the grid below, sketch a graph that could represent the disk's angular velocity. So again, we're looking at angular velocity from time 0 to time 1, which is the time at which the disk came to rest in part A. So the same time period. Okay, so we have the similar graph here. Okay, on the grid on the right, sketch the disk's angular acceleration as a function of time from 0 to t1. Okay, so same time period. Okay, well, we know that it still starts out with the same initial velocity, same initial angular velocity. Okay, so we can mark this here. And the other problem, it had a constant angular acceleration, and it went down to 0 down here, down to 0. But that's not going to happen in this case. In the first part of the problem, it certainly covers the same change in angular velocity. Okay, and it's a constant torque because the oil has not started dripping yet. But once that oil drips onto the contact surface, the disk may still slow down, but the friction is going to be reduced. So what that means is that its slowing is not going to happen at the same rate. So we're going to end up with some sort of a change in slope here, a change in the angular acceleration, which means it's going to have a change in the rate of angular velocity change. Now it's probably going to be a little curved, and it may move something like this. Okay. Now it's a minor change. We've shown a minor change here. You could change it a little bit differently, but most importantly, what you want to see is that it's not going to come to rest in the same amount of time because it took this amount of time to come to rest, but now because there's reduced friction, it's not going to get all the way to 0. Okay, so again, scoring wise, they're going to want to know that it's one slope here, a nice linear slope here, and some change in slope here that's going to mean that the acceleration has changed. Now it looks kind of subtle. I mean, you might see a graph that may look something like, much more pronounced. Okay, however, they want to see a slope change here. Now in terms of the angular acceleration, again, in the first half of the problem, we still have that same negative acceleration because it's causing the same change in angular velocity. However, as we drip that oil on here and reduce friction, we're going to reduce the torque and therefore reduce the acceleration. Now, we don't know for a fact that it's going to be linear, but you can assume that it's linear and it's going to move up towards the 0 mark because as we reduce the torque, reduce the friction, we're going to reduce the torque and therefore reduce the acceleration or get closer to 0. Okay? All right. Next question, or next component. It says the student is trying to mathematically model the magnitude of the torque exerted by the axle on the disk when the oil is present at time greater than 1/2. So we're talking about this time greater than 1/2 is this time here. Okay, so the second half of the problem. Okay, so the student writes down the following two equations, each of which includes a positive constant, C1 or C2, with appropriate units. So we have two equations, equation 1, equation 2. Notice we have the torque, we have C1, the constant, C2, the constant, then we have some time terms. Okay, now they want to know which equation better mathematically represents or better mathematically models this experiment. Okay, we got to choose equation 1 or equation 2. Well, what's happening here? We know that the torque over time is going to become lesser because we know the acceleration becomes lesser. We know that the rate of change of velocity becomes lesser, so the torque becomes lesser. So we want to pick the equation so that as time increases, the torque decreases. Now, I don't know what this constant is. I don't know what the units are. I don't even know if this term is actually correct or not. But what I can see is that if I increase the time terms, these t terms, and I multiply it by a constant, that means the torque is going to get bigger. So as time increases, torque increases. Now that's not what happens here. We know that as time increases, torque decreases. In this equation, we see if we increase the time terms, this time constant goes bigger, that means torque is going to become smaller. So the better equation of the two, not even knowing what those constants are, I can say equation 2 is the better equation because as time gets bigger, torque gets smaller, and that's in fact what happens in the experiment. Now it says to briefly explain why the equation you selected is plausible and why the other equation is not plausible. Well, you don't really need to get too elaborate here. In this type of question, when they say explain why, they mean 1 or 2 sentences with subjects and verbs that relate directly back to the description at hand. Now, you might write out full sentences. You might also just say in equation 2, as time gets bigger, and I'm just going to use symbols just to move quickly here. As time gets bigger, that means the torque gets smaller. Okay, and that's in fact what happens. In equation 1, however, as the time gets bigger, that means the torque gets bigger. Whoops, gets bigger, sorry. Now, we know that we want the torque to get lower because that's what happens in the acceleration, and we know that the equation 2 is the only one that works for that. Now, you might write a full sentence out with saying that as time gets bigger, torque gets smaller, and so equation 2 works. But that's essentially what you have to say. Okay? And that pretty much sums it up for this question. This will be a 15-point question. We can post the solutions online if we really need to, or talk about it when we see each other again. For your reference, this equation appeared on the 2018 AP Physics 1 exam. Okay, we'll see you back next time for more FRQ practice.